All right. So in the last section, I told you that in the course of energy conversion, when energy is converted from one form to another, um, it is lost to the environment. And I told you that anytime electron falls, it also follows. And that's where we came across H plus E minus, giving you hydrogen. And at that point, I told you, that was when I wrote this formula on the screen. H plus E minus equals hydrogen. Now, don't be bothered about this as chemistry. It's not chemistry, it's biology. Now, and I told you that the H plus is the same as proton. The E negative is electron. And the H is hydrogen molecule, or hydrogen rather. Now, that explains the reason that sometimes when we say that something gained an electron, instead of putting E negative there, we are going to put H there, because we know that anytime electron falls, it follows. Don't forget that. So every time electron falls, it follows. So that means when I'm seeing electron, I'm actually seeing hydrogen ion. Hydrogen, because if electron falls, it is going to follow it anyway. And when electron and heat couples together, we call it hydrogen. It's just like you say you had bought cookies, and you bought, like, let's say, candy. If the candy falls, it's not the candy alone that falls, the wrap also falls with it. So what you are getting is not just the candy, it's the candy and the wrap. And so the whole thing is what you have. And that means, that's what I'm saying here, that proton and electron is usually one. And what it forms is hydrogen. So anytime electron falls, don't forget that as a rule. Anytime electron falls, it follows. And they produce hydrogen. And that is actually the source of water molecule that is produced at the end of cellular respiration, which I'll show you. Now, so again, when NAD plus, which we said is the first electron acceptor, when it accepts electron, it will now make what we call NADH. So you see now, we didn't say it is becoming NAD plus electron. Now it will become NADH. We say that it has been reduced because when you gain electron, you have become reduced. So we'll say it has been reduced to NADH. So NAD plus, electron acceptor, reduced to NADH, electron carrier. Now, there are three major stages in cellular respiration. It's three major stages. If we want to put it in numbers, sometimes we say it is 4. But in the ideal sense, it's okay to think about it as 3. Now, the reason I said 4 is because if you look at it, you have some stages. You have the glycolysis, which is the first stage. We have a stage in between that we call intermediate processes, or pyruvate preparation, or pyruvate oxidation. It's really not a major stage, but it must happen. It's more like if you want to come to school, you have to get ready before coming to school. That getting ready may not be part of your itinerary, but it's something you have to do the coming to school, right? Now, so that's the way we need to get pyruvate ready, prepare it. So that stage is there. So that's the second. Then the actual second stage proper is citric acid cycle. All right. But the reason we have to do pyruvate oxidation is because Pyruvate cannot enter the citric acid cycle. So we need to change pyruvate into the molecule that is ideal for the citric acid cycle. I'll talk about that. Then the last one is the electron transport chain or oxidative phosphorylation. So let's go and look at each of them. Now, this shows you again the stages. You see, glycolysis is the first. You have pyruvate oxidation, then the citric acid cycle, and then you have the oxidative phosphorylation, which is the electron transport chain and chemiosmosis. I'll talk about each of them. They are very interesting stages. Now, this is the glycolysis. Think about the word glycolysis. It simply means breaking, lysing glucose molecule. So, don't forget, we are looking at cellular respiration, and cellular respiration simply means that you are breaking down the glucose molecule you have to make ATP. And that is what we say we are burning calories. And when you are done using up the glucose molecule, you need to heat again to replenish so that you have energy again for activities. So when we say cellular respiration, we are simply talking about when you breathe in so that you can harvest ATP from the glucose inside of you. All right? Now, look at this, please. Just be with me closely. This first stage is glycolysis. Glycolysis, breaking glucose into smaller molecules. This process will break glucose into pyruvate. Glucose is 6-carbon compound, and pyruvate is 3-carbon compound. Glucose is 6 carbon. Pyruvate is 3 carbon. So glucose is made up of 6-carbon compound, and pyruvate is made up of 3-carbon compound. So there are 3 carbons inside glucose. So what happened here is simply that the 6 carbon was splitted into 2 pyruvate. So 6 carbon was broken down into 2 3Cs, 3 carbon. That is what happened in first stage. What is interesting about the first stage, like you can see in the image here, is that it does not require oxygen. It happens in the cytoplasm, and there's no oxygen there, of course. So you see, it happened in the cytosol. No oxygen is required. But the other stages happen in the mitochondria, and we'll talk about that. This is going to make ATP, of course, but it makes limited ATP. In this stage, 2 ATP will be invested. 2 ATP will be invested in this stage. Invested meaning that 2 ATP will be spent. On the long run, 4 ATP will be made. Now think about it. If you spend $2 to make $4, what is your profit? You spend $2, and at the end of the day, you made $4. How much have you gained? You have gained $2. Thank you. So in the real sense, the profit made here is actually 2 ATP, not 4. Because 4 was what was made, 2 was what was invested. Now, we call this, I'm just explaining terminologies now, we've not started looking at it. We call this substrate level phosphorylation. The reason we call it substrate level phosphorylation is because it involves glucose, which is a substrate, a substance. And at the end of this stage, you are going to have pyruvate. This is just like a summary, okay? You are going to have pyruvate, which is still a substance. So the substance is what is going to come, to this stage. The substance will enter this stage, so we still have substance here. We still have substrate here. So we still call it substrate level phosphorylation. And I'm going to explain each of them. At the end of this stage, we are going to make ATP as well. At the end of the whole process, there will be no more substrate here again, no more substrate. What is going to come into the last stage will be electrons, not substrate again. All the carbon will have been gone. Because of that, we call this last stage, when ATP is made without substrate but electrons, we call it oxidative phosphorylation, no longer substrate level phosphorylation. So the reason these are called substrate level phosphorylation is because the ATP made there involves substrates. And think about it, what is the meaning of phosphorylation? Phosphorylation means addition of phosphate. And if you remember from the last part that I did, I told you that in your body you have ADP, which is the residual of ATP that was used before. Because anytime you want to use energy, you are actually using the terminal phosphate on the ATP. So every ATP have 3 phosphates attached to adenine. You have one phosphate, another phosphate attached to the adenine inside there. And I told you that anytime you want to use energy, you are simply using the last phosphate. This is what you send out. And when you send this, what is it going to remain? It's going to remain ADP, adenosine diphosphate. The way to generate ATP back from ADP is simply to add another phosphate to it. And you get those process. This is what does that process. And now it's going to be ATP. Where do we get the phosphate from? Food sources. You eat food that are rich in phosphate, and then that is how you get the phosphate. Now, this is what we call phosphorylation, addition of phosphate, phosphorylation. Phosphorylation can happen when a substrate is involved, in this case, glycolysis. A substrate is involved, citric acid cycle. Substrate is not involved, oxidative phosphorylation. So let's go. Now, look at this. How do we make ATP? The process that generates most of the ATP in the whole system, in the whole process, is called oxidative phosphorylation. The oxidative phosphorylation that does not involve substrate, that only involve electrons, makes more ATP than the glycolysis and the citric acid cycle that involves substrates. All right? So some ATP is also formed in glycolysis and citric acid cycle by substrate level phosphorylation anyway. Substrate level phosphorylation occur when an enzyme transfers a phosphate group directly from the substrate to the ADP to make it ATP. So it's more like this straight. It happens straight here. And then ATP is produced. That is what we call substrate level phosphorylation. Again, it involves a substrate, involves a substance, involves a glucose molecule or its derivative. We can use money as an analogy for cellular respiration. Glucose is like a larger denomination bill. It is worth a lot, but it is hard to spend it. ATP is like a number of smaller denomination bills of equivalent value, but they can be spent. The way you can use energy is when the glucose has been converted to ATP. Glucose will not give you energy by itself. It has to be converted to ATP first. ATP is the currency. It's all the same thing I think I was saying the last time, that if you need to buy something from McDonald's, you're not going to go with a check. You will need to break down the check. even though the check worth a lot, but you're not going to buy food in McDonald's with a check. You don't take check to gas station, at least as far as I know. Even though it has money, but you are not going to take it there. You need to break down the molecule to get ATP first. So cellular respiration cashes out in large denomination of energy, glucose, from the small change of many molecules of ATP. For each molecules of glucose degraded to CO2 and H2O by cellular respiration, up to 32 molecules of ATP are produced. So approximately 32 molecules of ATP are produced in this case. Again, there are three stages, majorly three stages, and then we have one intermediate stage. The glycolysis is the major, citric acid cycle is another major, oxidative phosphorylation, or which you see that they call transport chain, electron transport chain is another. Then in between, we have the pyruvate oxidation. Some textbook will call it intermediate stage, some textbook will call it pyruvate preparation. It's the same thing. Now, let's look at the first thing first, glycolysis. I call it glycolysis to let you know that it is glycolysis breaking down glucose molecule to release energy. So the first stage there is to break down the glucose molecule. And like I told you earlier, it does not require energy. ATP. Since it does not require ATP, it can happen in the cytoplasm. If it requires ATP, it has to happen in the mitochondria. But this does not require ATP, so it happens in the cytoplasm. And it has two phases. The first phase is the investment phase. The investment phase. And the second phase is the profit phase or payoff phase. That is the second stage. Now, in the energy investing phase, what is going to happen? You are going to use 2 ATP, which obviously is going to go ahead and spend the ATP. Now you are going to have 2 ADP left in the system. Now this phosphate is ready to phosphorylate the process to give energy for the process to proceed. The process needs energy. However, it's an exothermic reaction because it's giving off more energy at the end than what is invested, right? So in the course of that, so in the energy payoff phase, 4 ATP are now synthesized, 2 NAD plus are reduced to NADH. I will show you in a bit. The small sugar are oxidized to produce 2 pyruvate and 2 H2O. Now look at it. So at this point, all you want to do here, please listen to this. All you need to do here is that you want to break down this glucose. You want to break it down into 2 pyruvate to produce this. That is what you want to achieve. But to achieve that, you need energy to break down the bonds within the glucose. So we need ATP to break the bonds. So ATP was introduced as phosphate. In the course of the process, this process led to generation of 4 ATP, and now it also captured electrons. So NAD plus came in, and that's why we say that NAD plus is the first electron acceptor. So NAD plus came in, accepted the electrons, and I told you, anytime electron falls, it is also released, and that is it right here. That is it. Now, electrons was added, and obviously, since we have electrons and heat, it's going to now be H, hydrogen. And that's why you notice what we have here is H added to the NAD+. So NAD+ now became NADH. We say that NAD+ has been reduced to NADH. So we use the word reduced. it has been reduced. And that's the way I expect you to make your note. So NAD plus has been reduced to NADH. Now, NAD plus was called electron acceptor. Now, NADH is called electron carrier because it's carrying electron now. Because we know that when we see H, it means electron plus it. All right? Now, at the end of the whole process, you are going to have 2 pyruvates, which is our focus. You have gotten 2 ATP, and now we have some NADH. We have 2 NADH as well. Now we have saved 2 NADH. Now think about it in the back of your mind that when you have NADH, 1 NADH have capacity to make about 3 ATP. However, it's not going to make it until the final stage. We are storing it. It's like you are saving it so that you can take it along to the last stage. Now let's go. Just be with me. This will show you a view of it. However, I'm going to focus on the things I need you to focus on. The process is what I've explained already. It's just to show you the details now. So the first thing that happened is that you see this is the glucose molecule proper, complex molecule in a ring form, difficult to break down. You need ATP to break such down. So ATP is invested. That's the first ATP. Number 1 ATP. Invested. Now you see the phosphate here. Addition of that phosphate to the ADP to the glucose at this point. Remove this and then you see the phosphate there now. Now once this phosphate appear here, we call it glucose 6-phosphate. 6 because it's on carbon 6. Now, so the enzyme used there is hexokinase. I don't need you to memorize those enzymes. Then you have phosphoglucoisomerase, which is the enzyme now. What this enzyme does now is that it has converted glucose 6-phosphate to fructose 6 isomerase. What is the difference? The difference between fructose and glucose is the arrangement, structural arrangement. So you see that if you count the number of angles, you see the same number of carbon. The only difference is that the arrangement changes. All right? So you see it as rearrange it. Now, the next thing is another ATP is needed to break this down now. And the enzyme involved is phosphofructokinase. Kinase help to add phosphate. And that's why you notice that kinase is what is here. Hexokinase. Yes, phosphofructokinase. Kinase is the enzyme that helps to add phosphate to another molecule. So anytime phosphate is going to be added, kinase will be used. That's what I wanted to take note. Now, ATP then come, the enzyme phosphofructokinase. ATP is there. Now you notice another phosphate is added again to this guy, and now it became another phosphate here. This is now another phosphate. 2 phosphates now on this molecule. So it became fructose 1,6 because this phosphate is on carbon 1. This phosphate is on carbon 6. So carbon 1 and carbon 6. So now we have 1, 6, 2 these phosphates, meaning that we have 2 phosphates on this molecule and is a fructose. So fructose 1,6 by bis phosphate. So now glucose molecule is in the process of being broken down now. But now this is the phase when we are requiring energy. Then aldolase is going to hurt on this and make an attempt to split it. Now you have G3P. G3P is a 3-carbon compound. That's glyceraldehyde 3-phosphate. and you have dihydroxyacetone phosphate as well. It's also 3 compounds. So it's broke it into these 2 compounds. They are both 3 carbon compound as well, but they are not pyruvate. Our endpoint is pyruvate. Now, what is the next thing that is going to happen? This is now the payoff stage. In the payoff stage, we are not going to get ATP alone. We're also going to get NADH, which is the electron carrier. So now in the course of the process, glyceraldehyde, which is here, G3P, is going to be acted on by this enzyme phosphate dehydrogenase, and then see what is going to happen here. This has a phosphate on each here. You can see this is a phosphate here. Now this is the phosphate. Now what you will notice is phosphate dehydrogenase is going to add this phosphate, brought it in. Now then these now have 2 phosphate on it as against 1. Don't forget this has been splitted, so there's 1 on this G3P, there's 1 on this DHAP. So now this G3P now have 2 phosphates. So again, it became 1,3 biphosphate glycerate. Now, in the case of that, when this adds a phosphate, an electron is released. The electron is now accepted by NAD+, which is the initial electron acceptor, and then become reduced to NADH. Now, then the 2 ADP rather, that was in circulation previously, now came, then kinase, you see phosphoglycerol is going to come and add phosphate to this ADP, and now 2 ATP was formed in that state. Now, okay, I'll tell you something later. At the end of the day, so you see phosphoglycerol mutase is going to act on it, enolase is going to act, water is formed, and at the end of the day, you have pyruvate formed here. So 2 ATP was made, 2 ATP was made. Now 4 ATP was made in total, which made it 4 ATP made, but 2 was invested. So 1, 2 was invested, 4 was made. Now, at the end of the day, what have we made in the real sense in the whole of this process? Again, I don't need you to know the equations. I don't need you to know the enzymes. I just need to understand the process. What has happened at the end? The input, glucose, the output at the end of glycolysis, which happens in the cytoplasm, does not require oxygen. At the end of glycolysis, you now have 2 pyruvates, you have 2 ATP, and you have 2 NADH. Now, all of the carbon originally present in glucose is still accounted for in the 2 molecules of pyruvate, because we have 2 pyruvate, and a pyruvate is 3 carbon, and initially our glucose is 6 carbon anyway. So now you have only splitted a big 6 carbon compound into 2 smaller 3 carbon compound. Let me show you what has happened here in a little way to analyze it for you. So you have this carbon, 2, 3, 4, 5, 6. So all that happened in glycolysis is just like this. Think about it this way. It's simply like this. So this is a glucose molecule, underwent a lot of processes and produced 2 pyruvates and another pyruvate. So 2 pyruvates were produced. In the course of that, so now all that has happened is that a larger glucose molecule has been splitted into 2 pyruvates. In the course of splitting it, we needed 2 ATP to split it. but now we produce 4 ATP at the end. So 2 ATP is a product, is a profit. Then we also made 2 electrons. We kept electrons in 2 molecules of NADH. Now we have NADH that is a potential energy, but it's not energy. All right, so glycolysis does not release any CO2 at any point. So at the time when you have undergone glycolysis, CO2 is not released yet because you have not breathed in oxygen. Because it does not require oxygen, so you did not breathe out CO2 as well. So that means all the carbons are still intact. But listen now, what is the purpose of this story? The purpose of cellular respiration is for you to release all the carbon as CO2. So for you to have finished up all one glucose molecule, you must have breathed out 6 CO2. Because 6 CO2, we have 6 carbon in it. So each of these carbon will later be released as CO2. But that's the plan. But we don't have it there yet. We are not there yet because we have not broken down any of the carbon. We have just splitted the carbon, the glucose molecule, into 2. Now let's go. Now let's talk about the pyruvate oxidation. Now we have pyruvate. Listen, ideally we should go into citric acid cycle, but we cannot. Why? We cannot go into citric acid cycle because it's just like you want to go to nursing school and you just finish from high school. You cannot go to nursing school straight because you have to take some prerequisites. Because you must have taken some prerequisites before you get into nursing school. So the same thing, pyruvate should go straight into citric acid cycle, but pyruvate cannot enter the citric acid cycle. Why? Pyruvate is too large for the citric acid cycle. Now, the citric acid cycle can only accept an element that have 2 carbon, but pyruvate have 3 carbons. So we must remove a carbon from pyruvate before the element can enter the citric acid cycle. So let's go ahead. That's the reason for pyruvate oxidation. And that's why some people call it pyruvate preparation. Now, this is the issue now. So after pyruvate is oxidized, the citric acid cycle completes the energy yielding oxidation of glucose of the organic molecule. Most of the energy in glucose remains stored in the pyruvate molecules produced by glycolysis. All right. In eukaryotic, if oxygen is present, pyruvate will enter into the mitochondria to complete oxidation. This occurs in the cytosol of aerobic prokaryotics. Let's go. Now, let's go ahead and look at what happens in pyruvate oxidation or pyruvate preparation. Pyruvate, look at this here. I'll show you on this image and it will make very good sense there. Here is pyruvate coming here. Here is pyruvate. And you see that pyruvate have 3 carbon compounds here. Now, the purpose of this stage is simply to change pyruvate to become 2 carbon compound. So what's going to happen? So you see this TRANPOS protein here helped, and then in the whole of the whole cycle, let me show you this, then I'll go through the story. 1 carbon dioxide is lost, and it's lost as CO2 because you breathe in oxygen now because it's inside mitochondria. You breathe in oxygen now, and the oxygen will bind to 1 carbon compound from the glucose or from the pyruvate, and then it will release the carbon compound as CO2. So you have breathed out CO2 now. And that's why they say that when you exercise, you breathe faster and you burn more calories. It's because you are breathing in more oxygen is binding to the carbon, and you are breathing out the carbon dioxide. That is why we say you are burning calories during exercise, because you are breathing in faster and breathing out faster. Now, so pyruvate dehydrogenase is going to act on the substrate, and then coenzyme A is the enzyme that does this. Now, the purpose of coenzyme A, so is simply to join. Now we have lost one carbon dioxide, and that means one carbon has been removed from here. When the carbon is removed, what's going to happen? We now have 2 carbon left. So it's like this O is gone now. That's what makes the CO2, because oxygen binds to this. Now, in the course of it, electron was also released, and the electron that was released was accepted by NAD plus again. It became NADH. This is now electron carrier. One NADH was formed. In the course of this, now you see this has been removed, which is the CO2. Now this is gone. Let me see. I have eraser here. Let me try this. I can't clean what is there. All right. Now, in the course of this, I'm going to just shade on this. Now this is gone, because this is what we now have as the CO2. It's gone. You see, that's the CO2. So it's gone. So now we have just this left. Now, what is going to happen to this? This is what citric acid cycle can contain. It can only contain a 2-carbon compound, not a big pyruvate. And the 2-carbon compound is called acetyl. But acetyl cannot travel by itself. Like I'm in the office now, I can't come here by myself. I need to drive here. So when my car brought me here, so the car is the enzyme. So it has to bind to the acetyl, and now it is joined to the acetyl. So it became, the enzyme is coenzyme A. Another way you can shorten coenzyme A is to call it CoA. Coenzyme A is the same thing as CoA. So now when it joins to this, it now became acetyl CoA. Now, what is the function of this enzyme? It is not to do anything. It's simply to carry acetyl into the citric acid cycle. That's its job. The purpose of my car to bring me here is not to come into the office. I don't need my car. I've been teaching all day now, but my car does not have to be with me in the class. It's just to bring me here. Once it drops me at the garage, it's going to be there, then I come inside. The car does not need to get inside. So acetyl CoA is not going to go into the citric acid cycle. It's just going to take acetyl to the gate of the citric acid cycle. Once it gets to the gate, it's going to go back to carry another acetyl. But let me ask you one thing. Please answer this. Let me see the answer on the chart. How many pyruvate did we make from that glucose molecule that we broke down? How many pyruvate did we make? Thank you. We made 2 pyruvates. If we make 2 pyruvates, that means we have 2 pyruvates. So anything that happens going forward has to be 2, because it will be happening to both pyruvates. Now, if something happened to this pyruvate, it must also happen to this pyruvate. So if something happens to this pyruvate, it must happen to this pyruvate, because now we have splitted it into 2 pyruvates. Now, so this stage now, think about it as times 2. The next stage as well, we are going to say times 2. So if, for instance, now I tell you that we made 1 NADH here, what should you do? Times 2. Because it means that we are going to make 1 NADH with this pyruvate you are seeing on the screen, and we are going to make another NADH with the pyruvate you are not seeing on the screen, because we have 2 pyruvates now. So it will be times 2 for each of them. So if we make 1 acetyl-CoA here now, that means we actually have 2 acetyl-CoA from the glucose, because the big glucose is split into 2. It's now like a twin. All right, that's the idea. Now, so look at it now. Pyruvate is converted to acetyl coenzyme A before entering the citric acid cycle. So the purpose of all of this is to produce this guy, because this is what can enter the citric acid cycle, acetyl. Now, pyruvate hydrogenase, which is here, it will catalyze the reaction in 3 stages. Number 1, oxidation. You see, oxidation of the pyruvate, adding oxygen to the pyruvate, which is what gave us the CO2. So oxidation of the pyruvate carboxyl group releasing CO2. So now listen. We have lost one CO2 out of this pyruvate. We've lost one carbon. That means simultaneously too, we have lost another carbon from the other pyruvate. So how many carbon have we lost now? Can I see your answer? How many carbon out of the 6 carbons have we lost now? I'm expecting your response. We have lost one carbon from this pyruvate. So how many carbon have we lost from the 6 carbon compound now that we had? No, we have not lost 4. We have lost 2. Thank you. We lost one from the one pyruvate. We lost one from the other pyruvate. That means we have lost 2 out of the 6. We have 4 left. Does that make sense? So now we have breathed out 2 carbon dioxide. We have 4 carbons left. Because think about it, there are 2 on this acetyl, there will be 2 on the other acetyl. So that means we have 4 carbon left. We have only lost 1. Anytime a carbon is lost, it is going to be lost as CO2. So the next thing is going to happen is that we reduced NADH by the electron that was released. And then we reduce the NADH to become NADH. NAD plus to become NADH. I told you reduction. Then combination of the remaining 2 carbon fragments with coenzyme. This is what happened, the third one. Coenzyme added to it so that it can anchor it to the citric acid cycle. All right. So I'm going to stop this recording here and do the next recording on the next video.